Hello and good morning, everyone. Welcome to another episode of Alexa and Friends. My name is Jeff Blankenburg, and as we do every week, I get to bring an interesting guest on from the world of Alexa to talk about all the things they're working on, where they came from, and the future. So I want to welcome Ariya Rastrow. Welcome to the show, Ariya. Oh, you might be muted.
Yes.
There we go. Welcome.
Thank you. Yeah, good morning, good afternoon, good evening, everyone. I'm Ariya Rastrow. I'm a senior principal at Amazon and Alexa, and I'm happy and excited to be here. And I hope everyone enjoys this session.
I think they will. So one of the things that I like to do as we start these conversations is to ask you a couple of silly questions. And I haven't prepared you for these questions. You may not know what they are. Although I have found that previous guests have gone back and watched previous episodes to try to figure out what might be coming. So the first question I like to ask people, especially, for the last 10 or so years, we've had some amazing superhero movies that have come out in theaters. And one of the things that I always like to ask people is, if you could pick any one superpower for yourself, what would you pick?
A superpower for myself. I think if I were to pick a superpower, would be the ability to read people's mind.
That's a good one. Yeah. And so my follow-up question to that then, of course, is why? Why that one?
I think there are multiple reasons, but first of all, it would be very fun.
Oh, yeah.
Like if you're the only one that have that superpower.
Yeah. It could be good or bad, right?
Yeah, it could be good.
People thought it could be bad.
Exactly. Yeah. I mean, that's right. You know a lot who are your friends, who are your not friends. There are a lot of things about that. And the other part of it is that I love human interactions. I love human interactions, and I love getting working people on different levels. So I think having the ability to read people's mind would give me a superpower in terms of like building trust and interaction, like those interactions more meaningful, and be able to act quicker in interesting situations and awkward situations. Yeah.
Right. Yeah, I think that makes sense. I mean, being able to read people's minds has a lot of powers, and I think it would benefit anyone greatly. But yeah, I can definitely see that. All right, so that was my first question. Second one takes a little storytelling. But I want you to imagine, I know you and I are actually both in Seattle right now. We're just not in the same room. But as you think about walking down the streets of Seattle, there's a lot of very large buildings, right? And to walk around one of those buildings can take a little while. And you're trying to meet a friend at a restaurant, and you know that it's just on the other side of this block, and there's a convenient alley that you could go through that would take you right to the place you want to go. Now, it's a brightly lit day. There's nothing to be concerned about. You're not worried about crime per se. So you decide you're going to cut down this alley to meet your friends at this restaurant. And as you get about halfway down the alley, you notice at the end that you're heading towards emerges a giant horse-sized duck, really large duck, right? And it looks a little aggressive. It doesn't look friendly. And so as any smart human would do, you turn around, decide to go back the way you came, only to realize that end has been closed in by 100 duck-sized horses. So a bunch of very small horses. They too look a little aggressive. And so you are now trapped in this alley between these two choices. And you know that you're probably going to have a small scuffle, a fight, trying to get out of one of these two ends. Which end do you choose?
Which end do I choose? Right. It depends on the width of the alley. Can I?
Not very wide. You're not just going to run around.
I'm not able to sidestep that one.
No.
Person. Okay.
Some people have attempted to slide like underneath it, maybe. But that's up to you.
Right. I wish I could walk one of those. I mean, the single dog, to walk with to talk the other dogs through that. Like, give me a little bit of a slack. Let me go.
Oh, you're a master negotiator. I like
that. Yes. That's how I tell you. I love interactions. I love doing things, by working them through, and removing the burdens and contentions in the interactions to be able to converge.
Yeah. So I've heard I've asked this question to 50 or so people at this point. That is the first time I've heard about negotiation. I like that. We'll try to mediate the ducks and the horses, and we'll see how it all works out in the end.
Exactly.
Very interesting approach. I like that. I think it's telling. It shows a little bit about who you are and how you think about solving problems. So thank you for humoring me with my silly questions. The next step, the next thing that I'd really love to chat with you about is kind of where you came from. I mean, you mentioned your title at the beginning, and we'll certainly get in more into what you do here at Amazon today. But I always like to give people the journey, and for our audience, this is often their favorite part of the conversation. I love to hear about where you came from, where you went to school, where you grew up, if that's important, and any of the kind of major milestones that you saw in your career as you changed roles or changed companies, and how those had a formative path to where you are today.
Yeah, so I was born and raised in Iran, and it wasn't until I was about 21, 22 that I moved to the States to do my PhD. And
so you went to college in Iran as well?
Yeah, I did my undergrad, and then I started applying to PhD schools here in the U.S., and I got admitted to Johns Hopkins University, and I started my PhD back in 2006, I want to say. Yep.
Okay.
And during my undergrad, I majored in electrical engineering, and I actually got very interested in learning about signal processing, probability theory, and statistics. And in fact, actually, towards the end of my undergrad, I got actually the opportunity to learn about information theory, and I started getting some, taking some grad school, grad level courses in information theory, which is the bread and butter of everything communication today, and actually, in fact, we can talk about it a little bit if we wanted to. There are some synergy, very nice synergies between information theory and machine learning as the current form.
Awesome.
But I didn't really know about machine learning and AI per se during my undergrad, and it wasn't until when I started my PhD in 2006 at the Center for Language and Speech Processing, where I got the opportunity to work with Fred Jelenic, who is known as one of the pioneers in the statistical speech recognition.
Okay.
Some people actually refer to him as the father of modern speech recognition. And Fred had a huge impact on my, in shaping my career path, and also like my interest in speech recognition and ML and AI in general. And one funny fact was that it turned out that Fred and I had one thing in common, which is Fred was also by heart an information theorist. In fact, he was advised by Robert Fano, that he is a super famous information theorist, who was actually had done a lot of collaboration with Claude Shannon, the infamous Claude Shannon that everybody knows, that he was a pioneer and who wrote that very famous paper about channel capacity and information theory that changed a lot of things in the field. So that was interesting. So when Fred called me, I remember vividly that day, when I got admitted, he once said, like, I want to talk to you, like, see if you're interested in speech recognition, information theory, and like this. Said, like, Fred, you got me there. I know you. I would love to work with you. And that like, it was a half an hour, call.
Right.
Yeah, and it was an easy choice for me. On the other hand, like, the other opportunity that I had was that our lab, Center for Language and Speech Processing, was a multidisciplinary lab. Like, there were people from computer science, from computational linguistics, from electrical engineering, with different diverse set of skills and backgrounds, which actually helped me a lot into understanding a lot of different concepts. Like, take it from the signal processing that I already had known a little bit about undergrad, and then starting doing the speech recognition. I have one of the few of the best people in the speech recognition field around me. There were a few well-known professors that I worked with, including Fred himself. And on the other hand, since I was an electrical engineering, but I'm a major in electrical engineering, I wasn't really too expert and didn't know much about computer science. So getting exposed to computer science folks around me in the lab actually helped me shape a lot of things in terms of thinking about algorithms, data structures in an abstract way. Those are things that eventually become a powerful tool set for me to be able to apply them into speech recognition and ML problems. And by the time I joined Alexa in 2012, after I finished my PhD, latching onto my background in the speech recognition, I started with few folks on the engineering side and other researchers. We started building the speech recognition technology from ground up, and also because those early days when Alexa was in infancy and was a secret project, the team was very small. So the opportunity there for me was that I got to expose to many aspects of, designing the whole Alexa end to end on the architecture level, on the ASR, natural language understanding component, and other components that are involved in the whole execution pipeline. And then it gave me the opportunity to be exposed to this. And then eventually I got also interested, besides ASR, interested in the natural language understanding and then the conversational AI aspect. Those are some of the interesting problems and technical problems that we are today working on.
That's amazing. So you got in very, very early on the Alexa stuff. 2012. I mean that's 3 years before the first Echo launched.
Exactly.
That's amazing. So do you have any? Without revealing any secrets or anything, are there any kind of fun or interesting stories that you have from those early days?
Those early days, yes. I can tell you one funny story, actually. I mean, it's a funny and interesting in different ways. So when we started actually working on speech recognition for Alexa, some of you know, like the thing that we will have to do was it's called far field speech recognition, which is like we had to, which is a, solving far field is paramount for getting, Alexa successful. This is very different. At that time, people, using cell phones, like smartphones was becoming widespread. People started using some voice interfaces in terms of doing voice search. But the difference was that in the phone, you reach out to your phone, you bring it very close to your face and start talking. For following speech recognition per se, it was a different. The challenge was very different. We had to design a speech recognition such that like you could put your device like 30 feet away from you. Maybe there is a TV or background noise in your house. And it was paramount for us to make sure that the speech recognition in the context of far field speech recognition is very accurate and low latency. So the funniest story is that early days, we essentially created an advisory board, like very famous professors and researchers that are working on, speech recognition problem. Of course, Alexa was secret. We couldn't tell them what we are working on. But the goal was that, like, every so often we have some sort of meetings with them. We ask questions without revealing what we are working on. Funny thing is that these folks didn't know what we are working on. But one of the things that early on they emphasized on us is that, guys, with respect to speech recognition, whatever problem you're trying to solve and work on, make sure that you don't work on far field speech recognition. Far field speech recognition is inherently very super challenging problems and one that is not solved yet, and we don't have solutions for it.
My goodness.
Yeah. So you can imagine early on, we starting getting that feedback, but nice thing is that we didn't shy away.
Right.
Yeah, we were excited to work on that problem and eventually come up with a solution that we could go launch Echo with.
That's great. And so without revealing anything that we can't reveal, was there a trick? Was there something that, like a switch that we flipped that we were like, oh my gosh, now far field is so much better because of X, Y, or Z? Is that something we can talk about?
We can talk about a little bit about the things that we did that now by now there are known to people.
Okay. So
in a sense, we were lucky that when we started, this revolution in the ML AI and the speech recognition specifically was happening in terms of using deep neural networks. It turned out that at the same time, around 2011, 2012, people have started looking into new techniques of applying deep neural networks to a speech recognition task. And people have started showing that, at least on some of the benchmarks, that this is resulting in a huge improvements on the task that was known at that time. But like we said, like most of those tasks were close talk, not far field. So that's part of the story. We doubled down early on, and that was a good investment in building the infrastructure around building deep neural network technology in terms of infrastructures, algorithm, and using also backend AWS, because it turned out deep neural networks are very compute heavy. They thrive on data and compute, and I think the confluence of these three things,
right?
Getting a start, starting on work on deep neural network very early on, betting on them, having the AWS backend and infrastructure as the white matter, if you wish, of our backend, right. And then making sure, that we put a lot of effort into leveraging supervised and unsupervised techniques to apply those deep neural networks was a recipe for building far-field spatial recognition. Of course, I'm very simplifying this problem. There were so many technical problems on the way that we had to solve it.
I honestly feel like for a lot of businesses, and certainly some of the science and technology that we're seeing with Alexa, things like AWS, just a relatively infinite amount of compute and storage I think that unlocks so many different things, especially in the research world, where before that was a hard problem to solve. Is like, where are we going to store all this data, or how are we going to process this in a reasonable, cost-effective way? I remember when I was in college, which was in the mid-90s, the server farms that they had just to crunch numbers was just amazing.
Absolutely.
And now you can go to a website and just plug some numbers in and go.
Absolutely.
It's amazing. All right, so here's a good question. So you got your PhD, you got right out of school, you joined Alexa, but you've been here a while now, and obviously you've moved up the ranks a bit. But what drew you to Amazon? And certainly what's keeping you here? Now I asked that as an Amazon employee, so I know what keeps me here. I like the company, I like the culture, but I would love to hear more about kind of your perspective on that.
Yeah, and that's a great question. This is a one that I get quite often, because now I just marked my 9-year anniversary at Alexa / Amazon. Yeah. I actually, even internally, I get that question, what keeps you here? But let me start with what got me excited to join first. So when I mentioned, when I finished my PhD, I was quite convinced that, voice interfaces are going to revolutionize how we interact with computers and backend services. I was quite convinced about that. At the same time, working on the speech recognition technology, I knew that this is a challenging and a complex task. So one that like mid-size and smaller size companies would not be able to build from ground up. So I was quite convinced that when I did the interview, Alexa folks didn't reveal it to me that you're going to work on Alexa.
Right.
I knew it was ASR and speech related, but I didn't know the exact project. But I convinced myself that this has to do with Amazon, given AWS infrastructure and all the nice things about toolings on AWS, is going to be working on something that would become speech services for both on the consumer and business side, that it will federate and commercialize and if you wish speech recognition services so that everybody can use it in their services. Little I know that the first day I joined, I was exposed to this ugly cylinder, back then prototype version 1, that I was told that you need to make this short that when you talk to this device from 30 feet away, it's going to recognize you very well, accurately, with low latency. And the first thing I said, so it doesn't have a display. Most of the time, when you do a speech recognition on your phone, you see there's a feedback,
right.
Live feedback. You see the recognition output. So in case things are not working very well, you quickly can recover. You have your touch. You can fall back to other mechanism to fulfill your request. So yes, there's no display. Speech recognition has to work almost with 100% accuracy. So okay, let's do it. By the way, on the speech services, I wasn't also too off. It turned out that a few years later, AWS and us, we worked separately on building speech services and enabling others. So something that later become, people would know AWS transcribe service. At the same time, I was always an avid Amazon customer. So by that time, I had already, bought and ordered many books through Amazon. Fun fact is that the very first item I had ordered on Amazon.com back in 2006 when I got here and started my PhD was a book called The Statistical Methods for Speech Recognition, which was written by my advisor.
Oh my gosh.
Yes. In a sense, I had to read that book. Otherwise, it would defeat the whole purpose. Yeah. So, but I also, so that I mean, this whole magic of ordering online through, and getting everything on time, it was super magical for me. And then I was always amazed by the customer, focused company like Amazon. So that was another reason that I convinced myself that I want to take this risk. I don't know the project, but I want to be part of an amazing customer-focused company and potentially work on something that can delight millions of customers.
Yeah.
With regards to your question about what keeps me excited here, I alluded to this. Working on real world problems and working backward from customer needs and pain is super exciting and super interesting for as a scientist. And at the same time, there's still a lot of challenges remain within the speech recognition field, AI in general, and conversational AI specifically. Keep improving our low latency speech recognition, serving billions of interactions per week, and building this federated voice interfaces for our developers to be able to build on top of that, build new use cases and skills and scenarios for our customers. It's technically challenging, but it's very, very, very exciting. Perhaps, sorry, I thought I got logged out. And then now, I think you touched base on this with Nico a little bit last week. Now we are actually working on making Alexa even more conversational and natural in terms of we announced, turn-taking approaches, where we alleviate the need from the customers to say the wake word with each interaction, so they can, in a very natural way, barge in and start a request with Alexa. They don't even have to say, Alexa, do that for me. They can just say, turn on the light or order that one. So without saying that, it's very way more natural and conversational. So those are the So my bottom line is that the challenging, technically challenging problems is still there, and I'm quite excited to be part of the company that is delighting our customers through solving those challenging problems.
Yeah. So as we talk about difficult problems, I think that for years, even something which it feels relatively solved anymore, right? ASR, automated speech recognition.
Mm-hmm.
It still seems like there's probably more to be done there, but I think a lot of people look at that as like, oh, we're done. We've solved that problem. What's your perspective on that?
It's a great question. We have come a long way in getting speech recognition technology to the point that is, widespread, ubiquitous in many aspects of our lives. That granted, we should celebrate that fact. Yet, there are a lot of challenges remain. So I can talk about from few things specifically for speech recognition that I think personally start challenging and interesting problems. One of the things has to do with the multilingual and code switching. So it turns out in markets like India, customers are very creative and in mixing Hindi with English, and that puts a huge burden in terms of the challenge and the complexity on the speech recognition. So solving the code switching problem. Humans are really good. Once you know those two languages, you're really good on recognizing the mix of the languages, where they happen. So we are good at that. Turns out machines are still having tough time recognizing some of these creative ways that people mix languages. And for markets like India, this is essential, because otherwise we will not have a good customer experience for fulfilling their request. The other aspect of this is, there's still challenges in terms of, making a speech recognition accuracy, robustness, great for noisy and very challenging scenarios. You know, Alexa and voice assistants are becoming more prevalent outside of our home use cases, and you're using them on the go, where you're situated in noisy environments, and it turns out that we still have some work to do to make sure that the speech recognition is robust in these scenarios. Like the other aspect of this is that think about Alexa and in multi-party scenarios where like two speakers at the same time, they're talking to each other, but they're also like actively are having Alexa participate in their conversation.
Yeah.
Multi-speaker party scenarios put an extra challenge into on a speech recognition. Often, when you have multi-speaker scenarios, people have overlapped speech. There's crosstalk. It's not really like I'm talking to my Alexa only, so I'm very clear cut in terms of the boundary and the segments of my speech. People do talk over each other, and that overlap in speech and multi-speaker scenarios put actually an extra burden and challenge for speech recognition and signal processing per se. There are other things that also, we have come a long way in building, efficient learning algorithms that can learn both from supervised and unsupervised data. I think you talked with Nico about this, that how we use millions of hours of unsupervised data to improve the ASR recognition without having the need to have the human labels or transcriptions.
Right.
So that's one aspect of it. But the other part is that we're still doing most of these things in offline. Bringing those algorithms into an incremental and lifelong learning, it's yet another step that we have to take. Like, it turns out humans, we learn on the fly through our interactions with each other and environment. We keep learning and updating our beliefs, and both on the perceptions, like vision and speech recognition, if you will, also on the higher levels, semantic, understanding the intent or entities.
Right.
You keep learning. So that's another thing. So now that's another challenge, that how do you make sure that Alexa is capable of doing the learning on the fly. And then, by the way, there we have a lot of like implicit and explicit signals. So it turns out in the multi-turn and dialogue, as customers actually interact with Alexa, we do have implicit signals to know that if ASR and speech recognition, natural language understanding, was successful in recognizing the speech and intent. Or, like, for example, you start a query with Alexa and right away say, like, Alexa, stop. So that perhaps is a weak signal to tell you that there was something wrong in terms of either misrecognition or execution with respect to the previous turn. So how do you use those weak signals in multi-turn and dialogue and in execution to bring this flywheel into a lifelong and incremental learning?
Right.
And the other aspect of this is, of course, multimodal. So how do we use, like, humans are really good at, like, you and I, when we talk, in terms of turn taking to know if it's your time to talk or if it's my time to talk, we use a lot of clues. I mean, from a speech side, and also we use vision clues. Like, I'm seeing you. I know when you're about to, inject yourself into a conversation.
Right.
And and also from the visual clues, I mean, in conjunction with the speed, also know when you're about to finish your turn. So both in terms of understanding when you're about to say something or when you finished, there is a lot of signal in terms of multimodal, fusion between vision and signal. So,
yeah, and I think a lot of people probably see that. If you think about the pandemic and the fact that we've all been on video calls for the last year or so, it's really clear to a lot of people that it's much harder to participate in a conversation when people aren't aware of what you're doing, especially if it's an audio-only call. It's hard to interject yourself. It's hard to contribute to the conversation and interrupt because they don't know that that's coming, where when you and I are talking in person, it's so much more easy and obvious.
Yeah. And perhaps one more thing excellent point. And one more thing that I add is also, like, since you brought up COVID and pandemic, there is this also notion, the challenge in the speech recognition, that new terms and phrases and vocabulary is always being added to our dictionary. So I mean, back in March 2020, we didn't know about COVID-19 as a word, as a vocabulary, as a phrase. So, and it's paramount for us to be able to capture those trends, like from web or other external sources, to be able to inject those into our speech recognition system, because people started actually asking about COVID-19. What are symptoms about COVID-19? And if you cannot build a system that can quickly capture those trends and add them into the speech recognition system, you fail.
Yeah.
So that's another aspect.
Yeah, and even beyond big events like COVID, I mean, there's just the generation of slang that gets created and the new definitions for words. I know I'm going to sound like an old dad now, but when you hear kids talk today, a lot of times they'll say, instead of saying "I'm not lying" or "I'm not kidding," they'll use the phrase "no cap," which is I don't know where it came from, but the idea that they say that is now a new phrase that is being used to mean "I'm not lying," or "this is the truth." And it's just really interesting to me to think about how the engine behind the scenes has to start being able to recognize and interpret those things in context to be able to say, oh, this is actually what they mean by that.
Absolutely. We definitely, we have invested a lot of effort, and still going on, into making sure that we are nimble and agile enough, latching onto the learning algorithms that we have to capture those trends, new phrases and new vocabularies. And as you said, that's paramount tenet for our speech recognition.
So you mentioned Nico earlier, but I talked with Nico Strom last month, and we were talking a lot about on-device ASR, automated speech recognition, and some of the implications that has for our customers. And I know this is something that you use also. So I'd love to know, can you tell me more about kind of the onboard ASR? I know you hinted at it earlier, but I'd love to know more about that.
Yeah. So it turns out that, like we talked about, that having a reliable and low latency and fast speech recognition is essential for building the customer experience around on the conversational AI. And customers do expect that even if their network is choppy, low bandwidth, the speech recognition is still fast. And like in the speech recognition, specifically for Alexa, when a wake word is spoken we detect that on device, and conventionally we start streaming the audio to cloud to implement and execute a speech recognition. So it turns out that we have to send these audio frames and signal through the network. And like I said, sometimes the network is choppy. Your wireless might your network might be out of reach. Still, we have to make sure that the speech recognition works fast and reliably. So one of the recent trends, like perhaps last 2 years in speech recognition, is to move away from conventional methods, cloud-based speech recognition systems that essentially encode acoustic model and language model. Acoustic model is a component that understands acoustic clues in the signal and tries to match them to phonemes and words. Language model is a component that understands, so what are the sequence of words that are likely to be spoken to a device? Right. So conventionally, we use these two knowledge sources, disjointly and separately in a speech recognition, cloud-based speech recognition, to implement the speech recognition. So now, with the advances in neural network and end-to-end approaches, we have built systems that are capable of doing a speech recognition using one unified deep neural network, which encodes both language model and acoustic model jointly. The both are jointly encoded in the network, and these networks are capable of directly mapping and translating audio into sequence of words. Wow. There's nice properties and attributes that you gain through using these new techniques. One is that because you have a system which is jointly trained language model and acoustic model, you get far better compression and throughput per size. Meaning that if you were to design your speech recognition for a given size and a given memory size, your accuracy would be far better than the conventional system. This is especially important for constrained scenarios like edge and on device, where you don't have a lot of memory or your compute power is more restricted in comparison with cloud. So it's latching onto these new techniques, we are able to build speech recognition systems that are far better in terms of accuracy given those constraints. The other benefit of getting that we are achieving by using this end-to-end one neural network approach to solve the speech recognition is that we can apply well-known sparsification and compression techniques uniformly to the model. So besides the fact that the model inherently has a better compression abilities, we can further downsize the model without losing accuracy to even make the footprint of the model smaller and make them even more appropriate for constrained and challenging scenarios. So these are end-to-end. But besides that, we also this year at ICAST, we presented a paper that we have actually apply higher level architecture changes to the speech recognition to make it even more low latency and more efficient, the end-to-end system. So one of the things that in a speech recognition, actually for voice assistant we do today is that, like I said, so when you say the wake word Alexa, we detect that on device, and by the time we detect, we are behind because the customer already has said the wake word. Right. So now we start sending it to the downstream, which is the speech recognition, and start streaming the audio to recognize the subsequent the frames and words. But for privacy and efficiency reasons, we actually go back and reprocess that wake word segment in the speech recognition. So this is to make sure that there are sometimes rare events where the wake word on device wake word has false accepts. We want to make sure that the ASR, which is a much larger model, much higher accuracy model in terms of recognizing general speech, is recognizing and reprocessing that wake word to make sure that we get a second stage signal that wake word was really spoken there.
Yeah.
But on the other hand, this puts us in a toughest spot because we have to go back in time. We have a backlog. So we already have some sort of a latency that we have to catch up with because like wake word in general is in average is 1 second. We are 1 second behind with respect to the spoken signal. So one of the things that we presented in ICAST, we leverage this, knowing that the wake word was spoken, and we inject the topology in the neural network where it says, like, we know that the wake word is usually of a higher signal to noise ratio because people, to get their attention of their devices, they usually louder, more clear. Because like even when I talk to you, to get your attention, I latch onto some clue. I mean give you some strength in my signal to get your attention. So we know that it's lower perplexity. Like it's not as challenging compared to the rest of the signal. So we leverage that and we define different branches in our speech recognition neural network, which says like if I'm processing the wake word segment, let's do it with a much smaller branch in the network because we know it's low perplexity, it's cleaner signal. Why to spend a lot of compute? Yeah. So and then by the time we move to the intentful segment, we use our full blown higher capacity, higher compute branches of the network. In fact, we actually, beyond wake word, we generalize this method, and we're actually going to present it at InterSpeech 2021, where we say, look, it's not only about the wake word versus the rest of the audio. If you think about it, there are intermediate pauses in the signal. Intermediate pauses are not that challenging. There's not really much of a signal into it. So why to waste compute and power into processing them? So in other words, conventionally, when you come up with a compression and a size in your model, you design it in a static and fixed way, meaning every single frame that comes into a speech recognition is going to be processed using the same level of compute and processing power. We find that this is deficient. We can really actually be smarter than that, because when you want to go with the compression rates that are very, very extreme for edge cases, doing this compression statically put you in a very tough position in terms of the trade-off between speed, compute, and latency and accuracy. So we have a paper in InterSpeech 2021 where we actually create a general neural network that comprises of slow and fast branches. And what we do is that we teach that network to learn inherent clues in the signal to know that where it makes sense to spend more compute, where it's okay to use a much faster branch of the network and do the processing faster. So we are presenting that in InterSpeech 2001, and that's one of the works I'm quite excited about. And I also talk about a little bit that besides this higher level architecture, we do have we presented the work at ICAST this year that talks about new methods of how to apply better compression and sparsification mechanism to our deep neural network. And we actually presented the work where we use some of the folks on the call might know compress sensing algorithms to achieve better compressions rates in the speech recognition. So compressed sensing algorithm is a signal processing. It's a well-known tool in signal processing community, which is to reconstruct a signal and use some redundancy in the signal with a much lower dimensions and much lower compute. So we use that and apply that to deep neural network techniques to learn sparse models that actually result in a good amount of improvement in terms of the compute and latency.
Wow, that is super interesting to think about how that all works. All right, so one of the other things that you've written about is the idea between like blurring the boundaries between acoustic processing and language understanding. Can you talk more about how ASR is evolving around that?
Yeah, that's right. Last year, I think for ICAST for InterSpeech, I wrote a blog about this, and I think it was for ICAST. So, I mean, we know now of more efficient algorithms that are available to us as scientists and engineers. And so now it has become apparent that ASR is not just about focusing on speech of a particular turn. So conventionally, we would treat these turns like in a dialogue as isolated, and we just try to like do a speech recognition given the acoustic information in the turn.
Right.
The human brain doesn't really rely exclusively on acoustics to do a speech recognition. We do really use a balance of acoustic perception and also semantic level information to be able to carry the speech recognition task. And so we want the machines also to be like that. Let me give you an example. So if you're sitting in a bar, so if you and I talk in an environment which is super clean, we are able to carry the recognition of the phonemes and words in a very high resolution using acoustic signal. Now imagine a scenario: you're sitting in a bar, super noisy, and we are very good and latching on to the information which is encoded in our context and the topic that is evolving over the conversation, and use that to make our ability to recognize each other's speech better, despite the fact that the environment is noisy.
Yeah, so I can actually relate to this. Like I said, I'm here in Seattle, and I had a team meeting last night, and it was a happy hour after work, and we met at a bar, and I was speaking with someone in a very noisy environment. But on top of that, English wasn't their first language, right? So they were speaking English, but it was with their accent. And what I found, oh goodness, there's always something popping up. Give me 1 second while I maybe. Sorry about that. So what I found is that I knew, and it made me think about Alexa as I was having this conversation, but I knew at the moment that I was not hearing every word that this person was saying, and I certainly wasn't understanding all of them. But I was able, through the context of his body language and the words that I was hearing, to still be able to stitch the story together in my head and be able to participate in the conversation, even though I knew I was only getting about 70% of what he was really saying. And I think that probably is an example of that you're describing, right?
Yeah, excellent example. That makes it way more tangible. And so basically, yes. So now, we at Alexa, we are hard at work to make use of this contextual awareness over the course of dialogue, being able to carry context on the semantic and acoustic level to be able to improve the speech recognition. So that's to improve the speech recognition using the context. On the flip side, there is this also, notion that, conventionally, when we talk about the speech recognition and natural language understanding components, the interface is only text. So speech recognition recognizes the speech frames, it outputs them as in the form of token sequences, word sequences, then it passes down to downstream natural language understanding for us to be able to detect intent entities and slots. It turns out that there's also a lot of information encoded in acoustic, prosody, emotion, like your speaking rate and what have you, that can also benefit the natural language understanding task. So you see that like there are a lot of efforts in building end-to-end systems that have a fuzzy boundary between ASR and NLU, meaning that NLU have a direct path and access to the acoustic information given a turn and also over the turns in the dialogue context to be able to improve this end-to-end performance of a spoken language understanding. So it's really the boundaries are becoming fuzzy in a sense that you're not treating ASR as a standalone component, you're not treating NLU as a standalone component. You're trying to build networks and architectures that can jointly use context in the dialogue and context in the acoustic to do the end-to-end spoken language understanding. The other dimension about this contextual awareness that you alluded to is vision and multimodal, right? So we touched base on that a little bit. That, for example, especially in turn taking and understanding when the user are about to talk to a device, it turns out that there's a huge amount of information. If the user is in a point of view of the device with a camera, that gives us a lot of information about when they're about to start to talking to the device, and so the fusion of a speech and visual context and the context in dialogue gives us a lot of ability to improve a speech recognition system, but also building new CXs where we alleviate the need for people to say the wake word, and they can do interact with devices without saying the wake word.
Very cool. Wow. I mean, I think it's very interesting for a lot of our audience to hear this, because I think as we move forward, and a lot of the people that are watching are people that are on the developer side of things, right? So they're thinking about, how do I build interactive experiences with voice? And hearing some of this, the idea that we're eventually at some point in the future probably going to be able to take advantage of things like signals that are greater than just sound. I think that this is an exciting time as we look forward to, where things are headed and how a lot of this technology works. Because you're right, there is a ton of data in there, and I know that emotion recognition is one that is really important to developers. I think just the way that you're describing that, the way that we can start to piece these things together is an exciting future.
Yeah, absolutely. So getting those clues from the speech in terms of outputting them in a structured way for our skilled developers to be able to use them to create new experiences for their services, but also internally we use them to improve our core components accuracy, both in terms of speech recognition and natural language understanding.
Right. All right. So earlier we were talking about different languages, and you mentioned code switching when related to Hindi and English. And I know you have a paper coming out that talks about handling ASR in those instances where you have dynamic language switching. Can you kind of share with us your paper?
Yeah, absolutely. Happy to. 2019, we announced and we launched a feature which we enable our customers, multilingual customer, to add pair of languages to their devices and be able to interact with Alexa devices in a multilingual fashion. For example, you could set your device to English and Spanish, and on the back end, dynamically we would understand
Sorry.
No worries.
Too many computers all at once. Go ahead. Sorry about that.
Yeah. So you can set your devices to say like pair of languages, English and Spanish, and on the back end, as you interact with your devices without you having to explicitly tell us what language you're going to be talking to your device, on the back end, having access to the audio, we will detect and classify each query as English or Spanish. So the method that we use for that feature, it relies on running on two parallel speech recognitions, like in English and Spanish, because we don't know what language the current interaction is going to be about. So we have to run both, so that we cannot detect first and then do a speech recognition on that language, because that will be pure latency. And then we have this backend service called language identification classifier or service, which detects what is the winning language. And then once we know what language it is, we use the speech recognition output from that language and then do the full Alexa pipeline and execution. So it turns out there are some deficiencies and shortcomings of going with this approach of running two parallel ASR systems. Number one is running two ASR systems, which conventional and cloud, they're both large models, is deficient, especially when you want it's not very efficient, especially when considering scenarios that you have to build these multilingual scenarios on device and on edge. We don't have enough memory and footprint to run. We have hard time running one speech recognition system, let alone
right.
running two. The other aspect, the other deficiency is that by virtue of running two parallel disjoint systems, we lose the ability to be able to handle cases that are, like we talked about, they're a mix of languages. So in our case, like we have a system that is purely Spanish, a system that's purely English. So now if the customer have queries that is a mix of Spanish and English vocabulary, then we have to pick one. We cannot handle.
Got it. But it's that common problem where you're not going to get it right the first time, but as you continue to grow and learn, you can get better at recognizing that. So for example, if I had a house guest that spoke Japanese,
mm-hmm.
And they started living with me, over a short amount of time, it would start to be like, oh, that's Japanese, right? But it probably wouldn't happen the first time.
Yeah, exactly. And especially in the cases that there is mixed, like the code switching is happening, it is even more challenging. So basically, we presented a method that we proposed that, like, instead of running two parallel systems, using end-to-end system, we build a unified multilingual ASR system that is capable of recognizing, different languages, speech of different languages, and also detecting the underlying language ID. And because we are encoding these two languages into one network, that gives us the ability to be able to understand position and segments where the code switch is happening, being able to handle them more robustly. But also, it turns out that there is this, shared information between the languages, that what the notion that we call in machine learning transfer or transfer learning or inductive biases. It turns out that when you start building systems, unified system across languages, you actually start improving the recognition and performance for those languages that are on the lower resource, the languages that are harder, inherently challenging, or we have less amount of data for. Through building these unified models, you enable transfer knowledge between these languages, and actually you improve not only you get the code switching, but on the individual level, you get better performance.
That's super cool. And I will share with you, one of the things that is so interesting to me is just, like, I can just feel the excitement and the energy you have for this technology. It's infectious, right? To think about just how excited you are to solve some of these problems and the way that you're working through this. It gives me a lot of optimism and hope for the future of where things are going when we have people like you working on this team solving these incredibly hard problems.
Absolutely.
So the other thing I wanted to talk about, because I know you have a couple of papers coming out this year, is the idea of, like, recognizing personalized content in an end-to-end speech recognition system. So give us a little background on that one.
Yeah. So it turns out, like we talked, end-to-end systems, because they try from data and they have to do the direct mapping from audio to output. So some of the terms that are rare words or very peculiar are with low frequency in our supervised or unsupervised training data. So basic that would put these systems in a tough positions because we haven't seen enough occurrence of those terms. They're really not really robust in recognizing them. So taking contact name, when you're like you tell Alexa to call person X from your contact list.
Yeah.
It turns out people have really peculiar ways of referring to their contact names, friends, and like different way of like the way that they format the strings and write it, like write that contact name and then store that contact. This puts us in a very tough position with respect to speech recognition. On the one hand, customers understand that, hey, this is my personalized contact name. I have given access to it, that you have access to it. So I expect you to be able to recognize it robustly because you know it prior and ahead of time. On the other hand, these are very challenging. So what we presented is mechanisms that we actually latch onto, these personalized entities, and we sort of in the runtime decoder, we inject them into the end-to-end system, and we bias and help the recognition system to use these terms to essentially get a boost in terms of recognition. We show that we represented like few different methods, and we showed like we get a really nice boost in terms of accuracy and recognition over those personalized entities.
Very cool. Very cool. All right, so we are almost out of time. Actually, I can't believe we've been talking for almost an hour already. But I wanted to get your perspective on one more thing. So I know you came straight from your PhD to Alexa. And one of the things that I always like to do, especially when I'm talking with the folks from our science organization, is to get a feel for for people that are future scientists. There's a lot of folks that are tuned in here today on our science channels that are aspiring maybe to be Amazon scientists at some point. How is Amazon, in your opinion, different than academia, and what are some of the perks of working at Amazon as a scientist?
Absolutely. I actually get that question a lot from my friends and other people in the field too. So, I mean, let me get that out of the way first, that they're both great environments to do research. Yet, we have very different approaches and methodology to attack research problems. Specifically here at Amazon, like we talked about, we are very customer focused. We do customer focused research. We always work backward from customers, and we strive to work on problems that are real pain points, and for our customers, and otherwise it would delight our customers. In academia specifically, however, this direct tie to customer experience is at times missing. And we all know that the notion of the flywheel in ML and AI, how important it is to be able to create and improve ML and AI solutions. This is not to say that there is no value. There is still a lot of value for academic folks that working on individual problems and coming up with technical solutions there. But this is just to say that how important that flywheel, ML flywheel, is for us at Amazon. So the other aspect and the other difference is, for me personally, actually, was this notion of end-to-end ownership of the projects, right? So in Amazon, probably you have here, we create usually two pizza teams. They're small teams that own a problem end to end. And this is actually,
and just for those that haven't heard that term before, because I think that's a very Amazonian thing.
Yeah.
The idea of a two pizza team is that a team should never be bigger than you could feed with two pizzas. So I think it's a really nice measurement because it's a little vague, it's a little fuzzy, but it gives a good illustration. Thank you.
And to me, this is very rewarding, especially for those folks that are at the beginning of their career. You're junior, you're just starting, yet you're given this end-to-end ownership, which I found it very, very rewarding. The other aspect of this ownership and end-to-end project is that usually the problems that you work on probably a smaller scale, like those two pizza teams that we talked about, they contribute to a larger scope project like Alexa for us in
Right.
the speech recognition, or like Amazon Go for people who work on vision. This, working and being integrated into this end-to-end larger scope projects gives you two benefits. Number one is that you learn to think with an end-to-end mindset, which I found very interesting and important. Like by sitting next to people that like design the whole system end-to-end, you learn what are the implications of my ML and AI solutions in the service side, on the throughput, on the cost, on the latency, on the efficiency. So those are the skills that you get exposed to and you learn very early on by being integrated in a larger scope project. Number two is that also being exposed to this, end-to-end projects gives you the ability to work with different backgrounds and skill sets. Like you collaborate with people, project management people. You collaborate with a lot of engineers. A lot of managers, and that gives you gives you the ability to be able to understand what are the mechanisms that you can latch on to making sure that different voices and different diverse set of skills are heard in the meetings. How can you manage meetings that are like that include a lot of people with different backgrounds? We want to make sure that like there are sometimes discrepancies in terms of what people know and understand, but yet we have to make sure that the projects go with a good pace. We don't get stalled. Like, we make judgment calls during these meetings in an end-to-end way. We say, like, especially for those decisions that are two-way, like we have a mechanism. Even if we make mistake, we can fall back to approach B. We make quick decision. And then that also is very rewarding, because very quickly you build this set of soft skills, if you wish, that I found that they're as important, if not more important, in conjunction with your technical abilities and skills, to set you on a success path and make you successful in your career path.
Awesome. Well, Ariya, thank you so much for being here today. This has been an enlightening conversation. I really appreciate your time.
Happy. I really enjoyed it, and I hope everyone stays safe.
Yes. All right. So you guys can find a lot of the articles he's written, as well as a lot of the other information available from our Amazon Science organization at amazon.science. Just type that right into your browser. And I would recommend checking out the ICAST 2021 page for some of the papers that Ariya has released just recently. So it should give you more of a flavor of kind of the work that we do here in Alexa AI. And you can always go to Amazon Science, as I said, to see everything that's going on inside that organization. So I want to thank everyone for tuning in. Thank you for being here. We will be here again next week. And I hope everyone has a safe and healthy weekend. So thank you guys all for being here. Take care.
Thank you. Bye-bye.